we're back at AP Review. This is 2015 ABBC Free Response 3, and it's a table problem. So before we even look at the problem, it's really likely that you're going to be asked to do two things with this table. Number one, approximate the derivative of this expression, the derivative of v of t, by using old school slope between two of these points. And number two, you're probably going to be asked to approximate the integral of v of t on some interval in this window using LRAM or RRAM or MRAM or trapezoidal. So knowing that, going into a table problem, you're probably going to have to do those two things, means that you can probably just feel prepared for two parts of the free response when you see a table. So Joanna jogs along a straight path for time 0 to 40 minutes. Joanna's velocity is given by a differentiable function v. Selected values of v of t, where t is measured in minutes and v is measured in meters per minute, are given in this table. Part A, use the data in the table to estimate v prime of 16. No shock there. So we don't have t as 16, but we do have t as 12 and we have t as 20. So if we use those 2 points, right, so for part A, right, v prime of 16 is going to be approximately the old school slope, because remember derivative and slope are sort of the same concept, between the point at 12 and the point at 20. So v of 20 minus v of 12 over 20 minus 12, right? So that's a 240 minus a 200, so that's a 40, over a 20 minus a 12, which is an 8. So I end up getting 5, and that would be meters per minute squared, right? Because that's acceleration, meters per minute squared. So do make sure that you have the correct units. Or meters per minute would also be correct. All right, so part B. Using correct units, explain the meaning of the definite integral from 0 to 40 of the absolute value of v of t dt in the context of the problem. And then, here's the other part that was expected, approximate that value using a Wright-Riemann sum with the 4 intervals from the table. So, part B. So, when you integrate the velocity, you get displacement. But when you integrate the speed, which is the absolute value of velocity, right, this is the total distance traveled by the particle, or traveled, sorry, it's not a particle, it's Joanne this time, right? Joanna, sorry. Traveled by Joanna. That's Johanna. Sorry, I'm the worst at this. Johanna. During the time from t equals 0 to t equals 40 minutes, right? And so a couple things you want to mention. You need to make sure you mention total distance. You need to make sure you mention the time frame that you're given, right? Again, I said particle, and then I said Joanna, and then I eventually said Johanna, because apparently I'm really bad at reading. Anyway, so you could say she if you want to go with the safe bet, or they if you want to try and use something more gender neutral. All right, second part, so that's the first thing. Explain the meaning, total distance. Sorry, I missed one important thing. In meters, because they said using correct units, right? So total distance in meters. That's the third thing you're going to have to mention. So total distance in meters traveled by Joanna or Johanna or whatever her name is. All right, and then the second part of part B is actually estimate this using a Wright-Riemann sum. So the wild card here is that since you're absolute valuing V, these numbers are all either positive or 0, except this guy. This guy's going to be a positive 220 because you're not using v, you're using the absolute value of v. So I'm going to get that this value, the integral from 0 to 40 of the absolute value of v of t dt, is approximately, now remember when I do a Wright-Riemann sum, I use the right of the two endpoints. So on this first window from 0 to 12, the height of this is a 12, right? Because that's the height from one x or one t to the other. And then I use the right endpoint. So it's going to be the right endpoint, 200 times that 12, right? Plus, on this window, from 12 to 20, the right endpoint is the 240 times the width of that interval, which would be 8 because it's from 12 to 20. And then the next window, and this is where people tend to get it wrong, it's going to be a positive 220 because you're not doing the integral of velocity, you're doing the integral of speed, which is the absolute value of velocity. And that interval is 4 units wide because it goes from 20 to 24. And then the last one, if I use the right endpoint is a 150, and the width of that interval is a 16. Now, this is a non-calculator problem, so at the very least, you need to set this up so that if something goes wrong with your adding, you still get credit for the fact that you knew how to set up the Wright-Riemann sum. Some of them aren't all that bad. So this guy is just a 2 times a 12, which is a 24, and then 2 zeros on the end, right? So there's a couple different ways to do this guy. Honestly, I would probably just do the 320, and I'd add that to a 1600, so I'd get 1920, right? this guy's just an 880. Oh, that's convenient because that 880 is going to work out well with the 1920. And lastly, if I were you, it's up to you, but I would treat this as a 150 times 2 times 8 because 300 times 8 is a lot easier. That's a 2400. So I end up with a 2400 and another 2400. And then these guys together should be, I believe, a 2800. So 222 and 16. So I think I get 7,600 meters, right? So that's my approximation for how far she traveled. Cool. All right, so those are the two things that you should be able to expect just walking into a table problem. And then in this problem, an interesting thing happens. Part C and D have nothing to do with the table. So the only two things that I told you to look out for on a table problem every single time, well, they already happened, and now they're not even going to have us use the table again. Part C, Bob, totally different person, is riding a bicycle along the same path from 0 to 10. Bob's velocity is modeled by an equation, which I'll write out in a sec. Before I erase the table, I want to confirm I definitely don't need it. Where T is measured in minutes, B of T is meters per minute. Find Bob's acceleration at 5. Don't need the table for that. And then lastly, based on the model B from part C, hey, it has nothing to do with the table, so let's go ahead. So let's go ahead and do part C. So I know that Bob, right, so Bob has a velocity, right? So Bob's velocity is B of T, right? And again, I'm just going to make a note for myself that it's velocity because they went out of their way to call it B for Bob. So this is his velocity, right? Not his position. And what they want is his acceleration, right, at t equals 5. So the acceleration is the derivative of velocity, right? So I'm going to get 3t squared minus 12t, right? Once I know that, I need b prime of 5, which is a 3 times a 25 minus a 12 times a 5. So it's a 75 minus a 60. So I get that b prime of 5 is 15 meters per minute squared, right? Because it's acceleration. Cool. Part D, based on the model B from part C, find Bob's average velocity during the time interval. So if you want the average value of a function, you just integrate the function and divide by the width of the interval. So Bob's average velocity, right? Bob's average velocity on that window is going to be 1 over 10 minus 0, the integral from 0 to 10 of Bob's velocity, which was the t cubed minus 6t squared plus 300 with a dt, right? So I'm going to get a 1/10 in front of, when I integrate, this will be a t to the 4th over 4 minus 2t cubed plus a 300t from 0 to 10. Right, so there's two good bits of news here. First good bit of news is that one of my bounds is a 0, and that when I plug 0 into this polynomial, everybody's gone. So that's great. The second bit of good news is that the other bound is a 10, and 10 is one of the only numbers that's really easy for us to put to powers, right? So I'm going to get that this is a 1/10. So I'm going to get a 10 to the 4th, which is a 1 with 4 zeros over 4, right? Minus a 2 times a 1 with 3 zeros, because it's 10 to the 3rd, so that's 2,000, right? Plus a 3 times a 10, which would be a 3,000, right? And then minus a whole bunch of zeros, but I don't really need it, right? Like all of the bounds will be zeros if I clean them up. So what ends up happening is I end up getting, this is 1/10 of, so if you divide 10,000 by 4, you get 2,500 minus 2,000 plus 3,000, right? So this would be a 500 plus 3,000. So this would be a 1/10 times a 3,500. So I end up getting that his average velocity is 350 meters per minute, right? And double check that your units are right. Double check, all the little things about your math. If you also think about whether that's a reasonable speed, it does seem reasonable based on the table they gave us for Johanna jogging, right? I mean, I don't know enough about biking or jogging to know a reasonable speed per se. If my brain for a second when I was doing the math thought it was going to come out as miles per hour, and I was like, whoa, that guy is biking fast. But it's not. It's meters per minute. Based comparatively on how fast they said someone else jogged, 350 meters per minute seems reasonable.